What is this? What class is this?
Deep learning.
没有啊。不用分享，不是，应该没差，这没有。但是所有人都这么想的话，就对了。就是确实很难做，但我是没有看。 只是我只是在把做事情，做那样就是那样的状态。这个到毕业，这个快要期末了，就下个月他下把作为考模的。这个事情是。这个我以前说的一个这方面没有，就是一些偏导的概念。基本的那个什么，这三类方式，多用方式。他跟我讲。收入是往上走的，为什么？就是但是你也不知道你他知道你干什么，他会往下走的，没有很明确的话。但是这个人没跟他追求找的地方还是有。
Okay, sorry to be late. Okay, we have a lot to cover today, so I want to get started as soon as possible. Again, that makes it doubly worse when I'm late. But while I'm setting up here, any questions? Anybody has? No? Think about it for a second while I keep the monitor and projector going. Okay. Well. All right, here we go. So, part 2 of 2 on reinforcement learning. So, some big summary from last time. Just jam all the equations onto one slide and just call it summary. So, when we started talking about reinforcement learning, we introduced just some ideas from Markov decision processes. Important thing here is we talk about a policy. So, anyways, we have these things. We have our environment. It's described. It's a state space, so it's described by some state or states within this space, and then we have this notion of a policy that is a function that takes us from a state to an action, and this is what the agent is doing given where they are in the state, and they have an objective in this environment, in the state space, and they're trying to basically maximize their reward, maximize their cumulative discounted reward. And unlike how I tried to teach it last time, it's discounting in the future, not in the past. So an optimal policy maximizes the expected cumulative discounted reward. And the expectations are taking over anything that's a distribution. So if we're selecting if the action we choose is as a distribution, or we're averaging over that. If our transition probability, or the transition we make with that action is probabilistic, we average over that. So just anything in the formulation that's got that kind of characteristic we average over. Okay, so to be able to do some machine learning here, we defined a bunch of functions. These are all still in the area of Markov decision processes that have existed for a long time. So none of this is really like this happened in the last couple of years and everybody kind of figured this out. This is again, a good example of things that existed for a long time, and then all of a sudden we could estimate things way better with neural networks than we could in the past, and so they were applied to these problems and they seemed to work. So we defined things, a couple of these functions. We had the value function, which was the expected cumulative discounted reward given for a policy, given that we start at a particular state. So this is some way of kind of valuing the state in the state space. And then we had this idea of a q-value function, which is very much like a value function, except for this time it's starting from a state and an action on that state. Okay, and then we said, well, we're interested in the optimal q-value function. So this is a function that provides the maximum. So given a state and an action, this is the maximum expected cumulative discounted reward over all the policies. So given all the policies, this is the maximum that we would get for this cumulative reward, starting at that state and with that action. So notice that this is not necessarily like. Notice that for different state action pairs, it might actually be that a different policy, different policies are giving us the maximum expected reward. It's just, so this thing is, this thing is maximum over all the policies at each state in action. So it's something like think of it as like an envelope over all of these policies overall. Well, it's really over all the Q value functions, but think about it that, is over all the policies that they're competing. So it's just some way of saying like, if I start with this state, in this state and take this action, no matter, this is the best I could possibly do in terms of Q values, given all the policies that are available to me. Okay, and then the reason we were interested in that is that you can actually pick out an optimal policy from that. You can actually use that. If you have access to this equation or to the Q value function, then given the state that you're in, you can actually pick the optimal policy by picking the action that gives you the optimal value, or the highest value for Q star, and so that's a policy. You're using Q star to define the policy, and then that ends up being the optimal policy, pi star. So that's interesting. So these are just different ways of kind of getting at what it is that we care about here, trying to maximize this cumulative discounted reward. And then we sort of bumbled around on this Bellman equation, but it turns out that there's this recursive. So the optimal Q value function can be expressed recursively in this way, and it's not hard to see that this is the case, just given the way that the cumulative discounted reward is defined in the first place, right? This is something like, if I'm at state and action, if I'm in the state and take this action right now, then whatever action I do next, the cumulative reward associated with that is going to have some sort of I'm going ahead into the future, so I apply some discount gamma to that. So that's where this thing comes in. And then I have a reward associated with that. So this is like, this is the reward that I receive at this point, and it's associated with the action that I'm taking. So it's a reward associated with the action that I'm taking currently. So it's just, if we spend some time in this class, we could kind of push all the mathematical symbols around and kind of see that's the case. The intuition is like, if we do have access to these future values, then which we do through having this Q star develop or define on all of the state action pairs, then we have this recursive equation. And the reason why that even matters is that as soon as you have a recursive equation, if it satisfies some properties, i.e. if it's a contraction mapping, then you can actually get at this this optimal solution, so this thing that satisfies the recursive equation, by doing this iterative update process. So if I start anywhere with it, some Q value function Qi, maybe call it Q0 as the first one, then I apply the recursive part of the equation. I now get an updated Q value function. I do that across all the state action pairs. I get a new one. And if I keep doing that, and I'm a contraction map, I converge to something, and that something is that something satisfies the equation. And so you could think of doing this like just kind of in a straightforward way, by just calculating all the S and A, or taking all the S state action pairs, listing those all out, and then computing values for all the QIs, and then updating that for all the QI plus ones, and just keep doing that over and over and over again. The trouble is that for even modest sized state spaces and modest number of actions, that becomes huge, and it's really just too computationally intensive to do. So we say, hey, you know what? Instead of trying to do that, let's just try to learn the Q star directly, and we'll parameterize it as a neural network. And if we do that, then what we're trying to do is we're trying to, like this, using this recursive, the Bellman equation, the recursive equation up above, what we're trying to do is we're trying to make our current estimate of the optimal Q-value function. We're trying to in a batch, in an iteration, we're trying to make it equal to the. So like think of this as like the thing on the left. We're trying to make it equal to the update that we're getting from the recursive equation. So that's what. So we just have an actually like a very simple L2 loss here, where the target we're going for at this point is what this like update, this recursive part of the update is gives us from the previous set of parameters. So like that's from like the previous batch, so like we're at, we've been doing this, we sample a new batch, and we update the parameters given this loss function. The way that you do that is you have a square here, so you just take a derivative that's with respect to the parameters, and you get something that looks like this. So our update in our stochastic gradient descent looks like that. So lots of symbols, but in the end, it's really just saying like, hey, if we have access to the Q, if we had the Q star equation, we could actually always we can use that to get the optimal policy, and so there happens to be a recursive equation that satisfies a contraction mapping theorem. So hey, that's great. Let's now use that property and learn an estimate of the Q star.
So the distribution rho is known, yes? Distribution rho and also epsilon.
Yes, those are given. Yeah, so this epsilon is like, so these are just like samples of the state spaces you could get to, given the state that you're in right now, S, and the actions you could take from that state, right? So this is like a neighborhood that you could be in, and then this row is just the this is the actions that you can. This is like a distribution of the actions you can take from the state that you're in right
It's a
now.
joint distribution, yes.
Yeah, that's right. This is like an expectation over the joint distribution of all these things together. So like this, this part here comes from these expectations, and then this part here comes from these expectations. Yeah. Okay, so here you go. So this is the formulation of deep Q learning, and so deep Q learning is doing these like it's doing these mini batches of transitions, and the way you might kind of naively approach this at first is to say, okay, well, like here's a whole bunch of like human played games, for instance. Like say we're trying to learn a policy to play a game. So we have all these games. We just kind of like run through all of the frames of the game or how we situate it. Like the example we looked at last time was like take the current and then the previous 3 frames. That's input to a convolutional network that we eventually learn the Q values for. So from that state, so that's our state, the actions that we would take. So it gives us the Q values of those actions we would take. So the trouble with that is that you have like really correlated samples at that point, right? So like if you just kind of run these mini batches in that way, then whatever's happening in the next step is really very similar to what happened in the previous step, right? Because your games are like that, like they're not the state isn't changing drastically. They're just very correlated with each other. So that's a problem because that typically gives you really inefficient learning. Here we go. That gives you really inefficient learning. That means that like basically, the update that you got to your parameters, like at this time, is really similar to the update you'll get the next time, and you get the next time. You're not really kind of pushing out into interesting parts of space or learning something new.
you're learning something very localized after a while. So you don't want to do that. So, you know, something of an innovation that was made here was, and it's not too like hard to think that this would be a possibility, but is to do this thing called experience replay, which is just to like keep a table of all the transitions. You know, as games are played, so this is just some way of like maybe like thinking about this. Think of this as like making a big lookup table, and then randomly sample from those transitions. So instead of it being, you know, the transitions kind of linearly in time as the game is played, just sample these like IID over any games played. And now you have really decorrelated, like truly IID samples, and training goes a lot faster. Yeah, so you make better use of your data for training. Okay, so how does this whole thing look? This is the DQ learning with experience replay pseudocode. So we have a lot to get through today, so I'm not going to go through this step by step, but if you look at the slides that I put up in Canvas, you could just go through each one of these things here and see that, you know, there's this call out for each of these lines, what exactly it is. Okay, so moving on. Well, so first, just questions on that summary of what we did last time, and just adding in this experience replay. Have you heard of DQ learning before? Yeah, like if you'd read like AlphaGo or something like that, you know, this is a big component of those kinds of things. However, it's not the only way to do reinforcement learning, and it may at this point be like kind of one of the minor tools for doing reinforcement learning, doing deep reinforcement learning, meaning using neural networks to do reinforcement learning. What we'll learn today is the policy gradients and the reinforce algorithm, and this is, I think, what you will more commonly see used like in papers that are doing reinforcement learning. But like, you know, it's all like the context in which we do all these things. It's still the same. We're still trying to learn the policy, given, you know, states and actions you can take on those. Okay, and then this actor-critic models is just something we'll add on top of that. Okay, so policy gradient. So what is a problem with Q learning? Thoughts?
Slow conversions.
Yeah. This could converge really slowly. Our estimates could be really bad. You know, like we are doing a stochastic version of the update with mini batches, so it could be, you know, that could be a really bad estimate. And really, like this Q function could be really complicated, right? Like it's a function over a huge space. The state space, you know, think about how huge this might be for games, like all the possible pixel arrangements. This example here, where a lot of reinforcement learning is done, where you're trying to get robots to, like, you know, do things, actuate their motors to, like, say, grasp something like that. Actually, all the positions that this hand can be in are actually huge. They're really high dimensional, and then the possible next actions is also really high dimensional. So, like learning, you know, a function over that entire thing can just get super complicated super fast. And remember, it's really the policy that we're interested in. We're not really interested in the Q value function or the optimal Q value function in and of itself. What we really want is a policy. The policy is the thing that matters, an optimal policy for taking actions given the state. So why not just try to learn the policy directly? And that's what policy gradients are all about. So what does it mean? So what's the next part of this? Like, what's next on my slide when I say we're going to learn a policy? You've seen this like 10 times now, probably throughout this semester. We're going to learn a policy. What does this mean? Say about it.
Network.
And the network's going to do what?
Take actions to try to learn a policy.
The network is going to be the policy. Exactly. Good. That's what it means. So what it means is that we're going to now have neural networks that are the policies. That means there's going to be a whole bunch of parameters that we now have to learn. So now we have functions pi theta, where theta are the weights of the function. That gives us a whole family, right? So it's like, the way this usually works is, you kind of, you choose an architecture, and then that's, that architecture defines the family of policies that you can learn, and then, each of the different weight configurations is just another member of that family. And when we're learning, we're trying to find some optimal one of those in that family. Okay, so we typically need something to to define what's optimal here, to give us some sort of loss. And so, not unexpectedly, we're going to go right back to the expected cumulative discounted reward. This is again, decision markup process is the thing that you want to optimize in this world. And now what we're doing is we have a function j that is that, and it's a function of the weights. So this will now be that cumulative reward given the policy pi theta, right? So this is a function of theta. Its value is the cumulative reward given the policy pi theta. Okay, so really similar setup so far. It's just now that our policy, instead of being like implicit in the background, that we're going to sort of like get from our Q star when we're all done with that whole iterative Bellman equation process. Here we're just going to say, hey, we're going to learn the policy directly. So again, what's the policy? We should state this explicitly. The policy is a function from states to actions, right? So this is going to take in states, and it's going to spit out something telling us like what action to take. You can formulate this in different ways. We'll check out here in a second, but yeah. Okay, so right, this is what we're trying to do. We're trying to find the optimal policy. So how do we do this? What do we want to do? We're all neural networks experts. What are we going to do here? Exactly, except for we want to maximize this thing. If we do gradient descent on J, we're going to minimize the cumulative reward. So here we want to do gradient descent. And if we just put like a negative sign on that, then we'd be doing gradient descent. But yeah, exactly. That's like the whole point of this class, right? Is like what you really learn to do is like you see a problem, you're like, okay, I want to do machine learning on it, so I got to figure out, a loss function that I can optimize my neural networks with, and in which direction to go. And so that here we go. We're trying here to maximize J, the expected cumulative discounted reward. Okay, so how's this going to go? Well, J is our loss, so we want to take derivatives. We want to compute gradients of it with respect to theta. So yeah, so that could be that can be tricky in this case, and so what we're going to lay the groundwork for the reinforced algorithm. Okay, so that expected cumulative discounted reward can be written in this way if what we mean by tau is like this whole trajectory of state, then take an action, receive a reward, transition to a new state, take an action, receive a reward, transition. So this is like, yeah, so this tau is kind of this funny thing overall, like all these possible trajectories. Where we're following the policy pi theta. Sure, and that can be written like this if we had access to this probability distribution. Okay, why are we doing this? Well, we have to do a lot more math to see why. So we can differentiate this. And if this thing is convergent, we can just move this integral like exists, and we can just move this gradient underneath the integral sign. So now we're integrating something, but like that something p is probably really a tricky function itself to work with, and yeah, I mean, just it's probably something really difficult to work with. We just expect it beforehand that it's going to be difficult because it's over this trajectory space. So it's like mixing in this kind of this. So you're doing an integral over the trajectory space. So like these path integrals, and then you have this gradient with respect to the weights that affect the way that we transition. So I mean, it looks pretty simple up on the slide. But this in general can be a really tricky thing to do. But it turns out that there's some tricks here that we can apply that make this actually quite simple. And it will look kind of silly at first, but let me get through a couple of slides to explain. So what we're going to do is the following. So we rewrite this gradient of p in this way. This shouldn't feel like this should help much, but it ends up helping quite a bit. So this you can always do this, right? So like whatever you're taking derivative of, you can just multiply by 1, which is in this case the same function here, top and bottom. And then this thing right here is now the gradient actually of the log of p, right? You remember your rule of log, taking derivatives of logs. You get whatever's the argument of the log goes in the denominator, and you take the derivative of that same argument in the numerator. Okay, so it turns out that actually when we do this actually simplifies things quite a bit and allows us to estimate this through just Monte Carlo sampling, just in the sense that we just will sample some trajectories from this and estimate that integral in this way. Why is that? It's the following. So this function, this tricky function, or density p over the trajectories can be written in this way, where we have our policy theta, which is giving us actions given the state, and then we have this transition probability that is given the state and the action, we go to a new state. Okay, this is just like basic kind of Markov process formulation. So this is just how we calculate the probability over an entire trajectory as we work our way through state by state, because it's a Markov process through the entire trajectory. Okay, so now if we take a log, all of those products become sums, and importantly, the one thing that has that depends on the weights of our policy, I mean, like the only place where the policy really appears is now like an additive term on its own, and then all of the transitions are in their own term, and they're constant with respect to theta. So now when we take derivatives of that, we don't, the constants go away. And so we're just left with this. This should be like parentheses right here, right? So that's where the sum is right here. So now we just have this thing over here, which is actually now just a derivative of the log of our neural network, which this is something we don't have to deal with. We're essentially just taking the derivative of our neural network, something we know how to do. It's actually a log of our neural network, but that's okay. We don't have to deal with that. We're just going to add a log to the end and back propagate through log. That's something that we can take derivatives of. So that's good. And now, because of that, we can simply approximate. You can just imagine approximating our actual gradient through this term right here. This is just coming back to the original formulation